Well, we revisit Kepler's third law here in the study of orbits and taking a spacecraft from the Earth to another planet. We can make use of Kepler's third law a little bit to produce this, but just a little review, a little reminder. P squared equals A cubed. P is the period in years. A is the semi-major axis in astronomical units. This formula only works as we orbit the sun. So mathematically, you'd have to change a constant in here to do this for the Earth or some other star. So P squared equals A cubed with years in astronomical units. This is something we use in the solar system for objects that orbit the sun. So how is it that we can most economically take a rocket, a satellite, and come to Mars, orbit Mars, reach Mars at least? Well, we've drawn on here or I've not drawn, but this is from NASA, a little graphic. The blue orbit is the orbit of the Earth. The yellow is the orbit of Mars. So this is called the Hohmann Transfer orbit, and it's a orbit of least energy required to get from Earth to Mars. So we launch when Earth is here. Mars will be back, someplace in here, and by the time that the satellite gets out to the orbit of Mars, Mars will move forward, and we turn on the retro rockets and we go into orbit out here. The important thing to look at is we have an ellipse. We have an ellipse with here is perihelion near the sun, and out here at Mars is aphelion of this orbit. How could we determine the semi-major axis? As we'd like to calculate the period for the orbit, cut that in half, and that would be the transit time from Earth to Mars. How can we go about finding the whole long axis of this Hohmann transfer orbit, the red orbit? Well, we know from the sun to Mars is to Earth is 1 astronomical unit, and the sun to Mars, what do you think that number is? Now, it turns out it's 1.52 astronomical units. So we have 2.52 astronomical units all the way across this ellipse. And cutting that in half for the semi-major axis of this transfer orbit, the red orbit, is 1.26 astronomical units. If we bring in now P squared equals A cubed, the A is 1.26. If you cube that, you get about 2. What would be the value for P if you don't have a square root function on your calculator? Most easy is take a square root of 2. That gives us P. But if we just guess, 1.2 times 1.2, 1.44, not big enough. 1.3 squared, not big enough. 1.4 squared, pretty close. So roughly 1.4 years, that's the period of this orbit. The time to get from Earth to Mars is just half of that. We're not taking a full loop around here. We want the spacecraft to land on Mars or go into orbit around Mars. So we only do half of the period. That tells us the transfer time from Earth to Mars. So about 0.7 years, or that would be about 8 months. But that's the concept of the Hohmann transfer orbit. With our rockets, we create a new ellipse where we leave from, the Earth, is at perihelion in this orbit. And when we get to Mars, we're at aphelion in the orbit, not going out any further. The Hohmann transfer orbit saves money. It's more energy efficient. Okay, tides. The Earth has a body of water around it. This is extremely exaggerated as to how thick the oceans are, but we'll go with it anyway. And here's the moon. Why do we get tides? How many tides are there during the day? Well, from gravity, in the study of the law of gravity, we know the force of gravity depends on the distance between the objects. So if we consider 1 kilogram of water here, 1 kilogram of material at the center of the Earth, 1 kilogram of material over here, which one is going to have the largest force from the moon? Well, the one where R is the smaller number. So we get more force at this side of the Earth, and little bit less force here, a little bit less force here. The water is not being lifted off of the Earth. Instead, there is a flow of water from other places in the oceans to this position below where the moon is located in the sky. And we get that high tide, but water fills in. This is a very simplified model. It does not have continents in it. The narrowing of the ocean bed and so forth has a major influence on the strength of the high tide, how many feet above average sea level it is. But this is the general concept. There will be a high tide in between the Earth and the moon. But look over here, there's also a high tide over here. And what's happening here is the material here and at the center of the Earth feels a greater acceleration towards the moon and less acceleration back here. And the water again flows along the surface of the Earth and piles up in this opposite sense. Now the Earth is spinning once every 24 hours. So if you're some observer at the point of this arrow, the Earth's rotation will carry you to a region where there's high tide, and then low tide, and then high tide again, roughly 12 hours later. It's a little bit more than that because the moon is moving in its orbit, kind of a moving target as to where this bulge is located. So it's a little bit more than 12 hours from high tide to high tide. But you should realize roughly there are 2 high tides per day. There are 2 high tides, one on each side of the Earth compared to where the moon is located. So tides are produced by water flowing along the surface of the Earth, not from water being pulled off by the gravity of the moon. If we get an alignment where we have moon and sun together, then we can get a high tide that's a little stronger called a spring tide. That can happen for new moon or full moon. If we take a look at the tides when we have quarter moons, then the moon is pulling one way, the sun is pulling the other way, and it turns out that the moon has a greater tidal effect. The moon, of course, has less mass than the sun, but this tidal effect depends on the difference of force across the body of the Earth. And because the moon is closer, this difference is more important when we calculate the different size of forces from the moon. From the sun, there's not a big effect of distance going across the body of the Earth because the distance to the sun is so great. This graphic is completely out of scale. The sun should be very far off to the right, but there is more effect of the tides due to the moon, but occasionally we can get the moon and the sun cooperating and producing an extra high tide and low tide range. So examples here, this is the same location. You can see the cargo stacked on the dock here. High tide, low tide, and there can be quite dramatic changes in the sea level if the shape of the coastline is favorable. Over 50 feet range in where the water is located. So you have to build docks appropriately to account for that and not plan on going out in your boat at the wrong time of the day. So you read the tide tables that are local for each position. But in Canada, we have this Bay of Fundy with great changes in the level of sea level. From overhead view, again at high tide, water filling in here. At low tide, a lot of water has drained out, and you can see more of the kind of delta regions that are present there. The Earth exerts a tide on the moon, and it's gotten to the place where the moon is tidally locked to the Earth. So we only see one side of the moon. The moon is a little bit football shape, elongated towards the Earth. The moon does not have liquid water on it, but the moon was more molten and plastic in the past, and we have a kind of a little bit oval shape to the moon, and that the Earth's gravity keeps the moon from completely swinging around. If you can imagine a football with the point of the football pointed towards the Earth, if you rotate that football a little bit, the Earth is going to pull on that point of the football, try to bring it back into line. It's going to pull more strongly on the side of the moon near the Earth than the point of the football that's more distant. And this is a restoring force situation, and the moon is tidally locked to the Earth by this restoring force. It wobbles a little bit back and forth as it goes through its month, but the moon is not free to rotate at any speed that it might want to have. The moon is tidally locked, so it spins once on its axis for one orbit as we view it around the Earth. Tidally locked because of the Earth's gravity, not allowing this, and football shape is complete exaggeration. The moon is not distorted that much, but a little bit of football shape. The point of the football towards us is more strongly attracted than the point of the football away from the Earth, further from the Earth, and we have this force that keeps the moon pointed towards us, this near side with the craters, sort of the Maria, the big Maria, and some craters that are notable. We always see them every night of the month if there's light available to see them. So here's a drawing that illustrates, again, gross exaggeration, but this red oval here, there's a stronger force on this side of the oval from the Earth's gravity compared to over on this end of the red oval. So the Earth's gravity swings the moon back in line, overcompensates, or from inertia the moon keeps rotating a little bit until the force of gravity starts bringing the moon back into line again. But we have this tidal lock. It's due to restoring force acting on the moon by the Earth's gravity. So there are other points in there that you should be reading about and asking questions on. There is I'll probably mention this a little bit, an effect on the Earth of this water moving back and forth. There's a friction that takes place, and the Earth's rotation is slowly slowing down. Not very dramatically. I think our online textbook says something like 0.0016 seconds per century. The Earth's rotation is slowing down, but it is a measurable effect over millions of years. There are corals that have a growth pattern that has a daily component to it, sort of like tree rings, but there's a daily component and a more seasonal component. So those rings can be counted, and in the past it appears that the Earth was spinning more rapidly, such that we completed one rotation in 22 hours instead of 24. So this friction of the tides is having an effect. The other consequence to this is that as the Earth spins a little bit more slowly, physics says something has to compensate for that, and what compensates is the orbit of the moon. The moon is moving away from the Earth, and I don't have it written down, but I think it's about 1 inch per year that the size of the moon's orbit is increasing, about 1 inch per year. This can be measured from equipment left behind on the Apollo moon landings, mirrors that kind of act like bicycle reflectors. We'll talk more about this when we talk about the moon. But the tides have a great effect on fishing industry and people and using boats. The tides slow down the rotation of the Earth, and at the same time the moon's orbit size is increasing. All this because of the tidal interaction. So with that, I'm going to let you read the book and write down questions and bring questions to class.